Let me know what do you mean by binary trees, or let us start with the definition of trees first. Tell me that. What do you mean by a tree data structure? So far, whatever we have encountered, right, all were linear in nature. Am I correct onto that?
Yes, yes.
What kind of data structures we have seen so far? Let that be arrays. 1, 2, 3, 4. Elements are arranged one after the another, right? This is the
Yeah.
sequence of arrangement. You have taken stacks again. You have taken stacks. So what is happening is on the top of another data, a particular data is being inserted. From the top only it is getting popped out. Correct? So one, again, can I just say, this is nothing but from bottom to up or top to down, the arrangement of data somehow is looking like. Okay, we have seen queues as well. So again, if I say here, it is in between front to rear. Correct? One after
Yeah.
the another, again, the sequence of data is. Okay, afterwards, linked list also, even if the memory management is not continuous in nature, but still one after the another only we keep the data points. Correct? So in all these kind of data points, what is the commonality that we are getting? What is the
It's linear.
commonality? You draw just a straight line, right? You draw a
Yeah.
straight line. All the data points would be falling into that. So that's why they are called linear in nature. That's why they are called linear in nature. Data is being arranged one after the another. What about trees? So see, whenever we are transiting to the topic of trees, these trees data structure are non-linear in nature. What do you mean by that then? Non-linear.
It should not be derived from single line.
See how the structure of trees look like. They are again in terms of nodes only, right? They are
Yeah.
again in terms of nodes only. One is there, but a particular node can have multiple other connections. This is my node. One is connected to node 2 and node 3. Correct? Again, further, suppose 2 is connected to have 4, 5, and 6. 3 more nodes it is connected to. 3 is connected to no nodes at all. So if you start off from 1, right, how many paths do you have to take? It's no longer that if I just draw a straight line somehow like this, I'm going to get all the data inside the straight line. Not possible. I have
Yeah.
to draw multiple curvatures, something like this, something like this, something like this. Then only I would be able to reach each and every data of the structure. Correct?
Yeah.
Fine. So this is what we call as a non-linear data structure. Correct? A particular node can have multiple paths to visit. A particular data from a particular data, I can try visiting multiple paths to access each and every data that is kept here. So that's why we call them as non-linear in nature. Correct? Okay then. So my point is right now, can you try defining trees in some time, in some terms, whatever you already know about trees, the tree data structure? How would you try defining it, the tree data structure?
Tree start from top and goes down.
Okay, basics. What are trees made up of? Tree data structures are made up of what kind of entities? I think
Root.
they are made up of nodes and edges. Am I correct?
Yeah, nodes and edges.
Most basic thing. They are made up of nodes and edges. So a particular node can have multiple other attached nodes. Correct?
Yes.
Okay, then. So let that be 4, let that be 5, let that be 6. Suppose somehow this is my tree is looking like. Correct? Okay, there
Yeah.
is no, as of now, in general, if you take the definition of in general tree, there is no boundation. How much a particular node is getting connected to how many nodes? Nothing as such. It can have attachment to n other nodes. Okay, in general, if I take any tree, it can be typically attached to n number of nodes. Any node can be attached to n number of nodes. Such kind of tree is what we call as an n-ary tree. Okay. Now tell me for one thing. Let's talk about some of the properties of a tree. Tell me for one thing. How many nodes? If there are n nodes inside a tree, if the number of nodes are n, how many edges it should be having? How many edges it should be having? Tell me that.
1, 2, 3. N plus 1.
It is always exactly equal to that of n minus 1.
N minus 1.
If you are having n nodes, the number of edges inside a tree are bound to be n minus 1. It cannot be less, it cannot be more. It is bound to be n minus 1. Getting it, all of you? Inside a tree, there are exactly n minus 1 edges. Fine. Okay, then. What are the other properties of a tree? Let's draw a tree, small tree, whatever I'm having here. 1, suppose it is connected to 3, 2, 3, then again it is connected to 4, 5, and so on. It is connected to 6 only. This is the tree that is looking like. Any Any other properties that you can think of seeing the structure? Think a tree is always connected. You start off from any node. I start off from 5. I try to visit any other node. Will I be able to go? Will I be able to visit any other node from 4 here? Tell me that. Will I be able to visit 4 from 4? If I start off from 4, will I be able to visit any other node inside the structure?
No.
Why? I can take, if you wish to reach 5, you can go to 2, you can reach 5 then. Possible. If you wish to reach 1, right? 4, 2, and 1, you can try visiting. If you wish 3, okay, fine. I can try visiting 2, 1, and 3. This is the path. Okay, again, then 4 to 6. There is again a path. 2, 1, 3, 6. So what we are getting here? Any node X is connected to any other node Y inside a tree. So that's why a tree is fully connected in nature. A tree is fully connected in nature. If you let me know that, okay, fine. What if I try to get a structure something like this? 1, 2, 4, and 5 is here, right? 1, 2, 4, and 1, 2, 4, and 5 is there. And afterwards, suppose 3 and 6. Then let me know, is the structure still a tree for us? A non-continuous structure for us. Is it still a tree for us? Yes or no?
They're two different trees.
Exactly. They are two different trees. But as a whole, if I consider that as an entity, then
No.
no, definitely not. Because if you say, okay, entire 6 nodes are a part of a single tree, from 4 to 3, there is no path. From 4 to 3, they are completely disconnected. So that's not the nature of trees. A tree is fully connected in nature. Any node X is connected to any node Y. Any node X should be reachable from any node Y, as well as any node Y should be reachable from any node X. That's the nature of tree. It's fully connected in nature. There is no separation that's allowed. What kind of structure is this? If I just go ahead and say, let this be a single unit of entity, then what kind of structure will it be called as? A structure where there would be a collection of nodes and edges for sure. But the fact is, there can be some discontinuations. Such kind of in general structures are what you call as graphs, where discontinuity is allowed. Still, the particular two different components, whatever I'm having, they are part of a single graph only, but they are discontinuous. This is my component 1. I can just try assuming this is my component 2. Two different components comprising of the same graph. Okay. So what I can say is that a tree is a special kind of graph with some constraints. Every node has to be connected to every other node here. Every node has to be connected to every other node here. Okay, then let me know another thing. From 4 to 6, does there reside a unique path only? Tell me that. From 4 to 6, if you visit from 4 to 6, that's the only way from 6 to 4 I can trace back. Is it the observation we are getting as per the structure here?
Yes.
Okay. So again, another property of tree is there lies a unique path between any two nodes X and Y. There would be a path and the path would be unique in nature. And the path would be unique in nature. Getting it? Getting it? Okay. Then if I say, okay, can you try thinking in some manner that, fine, what should I do in order to break the unicity? I don't know. I don't want that the path in between any two nodes here that is comprising of the tree should be unique. There should be yet another alternate path. Then what should I do in that case? Anything that you may try doing with the tree itself.
We can have one more node from 1 to 4, say, and 4 is again pointing to 6, something like that.
Okay, suppose I say that, let us suppose 6 is connected to 5. Works?
Right. That
okay, 6 is connected to 5. Okay. Then tell me that one thing. Is it still a tree for us?
No.
Why? Is it breaking the nature of? Is it breaking our first property, n-1? For n nodes, there has to be exactly n-1 edges. Correct? So again, is it leading to a cycle for us? Tell me that. 1, 2, 5, 6, 3. Is this comprising of a cycle inside a tree?
Yes.
Okay, if you start off from 1, there is definitely a path. I can visit back 1 itself. Whatever may be the nodes that are comprising of the cycle, you start off from them. There is definitely a path using which I can visit it back. Okay, that's the definition of a cycle. So another thing that you are observing is, if suppose there are n nodes inside a tree, I try somehow to make n edges as well, I am getting a cycle. So definitely a cycle is in existence. Cycle is not allowed inside a tree. Getting it, all of you? Getting it? A cycle does not exist inside a tree. If the cycle is existing, the structure is not a tree at all. Fine? All fine till here? Tell me that. All fine? All fine? Is it clear? Inside a tree, there are n nodes and n minus 1 edges. Any two nodes are connected. There has to be a unique path in between x and y. Correct? Duplicate paths are not allowed. Okay. If you go ahead and try implementing a duplicate cycle, right, you may come up with something called as a cycle in between the nodes, right? And if there is a cycle, it is breaking the first property of the tree, n nodes and n minus 1 edges. Fine. So a cycle shall never exist inside the structure of a tree. Getting it? But in terms of a graph, the cycle is fully allowed. But in terms of a graph, it is fully allowed. No such thing inside a graph that if there are n nodes, there has to be n minus 1 edges. Nothing as such. There may be zero number of edges. There may be some maximum number of edges that can be associated with a graph. Okay. Are these things clear for everyone? Tell me. Whatever we have discussed, are these things clear for everyone? Tell me that. Are these things clear? Any doubts you are having, let me know. Hello.
No, it's clear till now.
Yeah.
Okay, let's move on then. Okay, so in general trees, we have taken a few of the properties, right? Right. If something comes up, then I'll take that later on. So what are binary trees in our case? The area of specificity. Binary trees. Can you try defining it? Do you know about the definition of binary trees? What is it, by the way? How do
It's
we
a
define
special,
binary trees?
I think, special type of tree which is sorted in nature. Like
Nothing as such. Binary trees are what? Again, they are
Binary
trees
trees
only.
have only two nodes.
Okay, see. See for one thing. Some analogy, let us take that, right? If this is my tree, if suppose there can be, fine. If this is my tree, right? Any of the node I am having can serve as the root of the tree. So let for me, the topmost node that as per my structure that I have drawn, let that be the root, the start point of visiting each and every node. Do remember that inside a tree, whenever you try defining that, there has to be a root from where the visiting of entire node start off. You start visiting or accessing the entire tree nodes from the root itself. That's the core of the tree or the head of the tree that I can try visiting. Okay. So if root node is the topmost node inside the entire hierarchy, whatever I'm having, right? What are the bottommost node in the hierarchy called? Can you let me know? Root node is the parent of all nodes. Okay. Root node is the parent of all nodes. If that's the top of my hierarchy, then at the bottommost, whatever nodes I'm having, what are they called?
leaf nodes.
Yeah, they are what you call as the leaf nodes. Correct? Okay, fine. If I ask you, are this is this 4 and this 5 also the leaf? They are also leaf nodes? Or only the 4, 5, 6? The last level nodes are the leaf nodes for us.
The last level.
No, not at all, right?
Okay.
Leaf node is what? Leaf node is what? What is a leaf node? If any node is said to be leaf, right? Then what happens is that it does not have any left or right child.
Right.
Okay. This leaf node cannot have any child node. This leaf node
Yes.
cannot have any child node. So another analogy that would be coming up is, if currently I'm standing off from my current node root, then from root down the level wherever I can go, these are all the child nodes of the root. Getting it? These are all the child nodes of my root. Okay. How to define the child nodes? If suppose you are right now standing at the root R, from here, whatever nodes down the level I can go to, C1, C2, C3, C4, and C5, they are all child nodes of the root. They are all child nodes of the root. Further, if suppose C4 and C5 are visitable from C1, then tell me what which node is the parent of C4 and C5? Can you let me know? Can you let me know? Root R is the parent of C1, C2, C3, and whatever child nodes are there into the next level. Now tell me for one thing, C4 and C5, it is the child node of what particular node?
C1.
Yeah, C1 is the parent of C4 and C5. So can I say root is the grandparent of C4 and C5? Can I say that?
Yes.
Okay, yes, fine. So see from one thing, the immediate node from where the next set of nodes can be visited, this particular upper level node serves as the parent. Okay, and whatever nodes have got visited, they are the child nodes of the parent. Got it? These points are clear for everyone. These points are clear for everyone. Let me know on this. Till here, is it clear?
Yes.
Okay, now let me know one thing. If root is there, right? Suppose that it has C1 and C2 as its child node. C1 has further C3 and C4 as its child node. C2 has further C5 and C6 as its child node, right? If I just isolate this particular continuous segment, what is it called? Can you let me know on this? Entire structure is a tree. Entire structure is a tree for me, correct? If I just say, okay, isolate this part, a continuous segment again that is starting off from C1. What is this continuous segment called?
Subtree.
Exactly. This is what you call a subtree. Just like, can you relate that with the topic of subarray, with the concept of
Hmm.
subarray? A continuous segment of an array, right, that starts off from a particular index. That is what you call as a subarray. Similarly, a particular continuous segment inside a tree that starts off from a particular node, this is what you call as a subtree. How can you define it? This subtree is rooted at node C1. Getting it? What is the root of this subtree? C1. Fine? Fine? Are these points clear? So tell me for one thing, if I take out this subtree, what is the root of this particular subtree then? Tell me that. What is the root of this subtree?
C2.
Okay, so this is again a subtree that is starting off from a certain node. The start point is C2. So I would be saying that this node is rooted at C2. Okay, what about, can a subtree has just a single node? Is it possible? Can a subtree have just a single node? Is that possible? Fully possible, right? These are leaf nodes in our case, C3. And I would be saying this subtree has just a single node, the root itself. That's it. Just like inside a subarray, right? We can have just a single starting element. Nothing else is a part of it. Similarly, inside a subtree, right, a node, only a single node can reside, and that would be termed as its root. Fine. Are these points clear for everyone? Are these points clear for everyone? Tell me that. Are these points clear? Let me know.
Yeah.
Okay, fine. Okay, then what are binary trees then? So suppose that binary tree has its root again, correct? Any root, in a sense, I'm saying, right? The tree may comprise of the main root and the subtree's root. Okay, there may be multiple subtrees of a single tree corresponding to any subtree, right? Corresponding to any subtree, there would be a root. Now, if I am saying that inside a binary tree, any root R has what? Any root R should be having either 0, 1, or at max 2 child nodes. Getting it? What are binary trees? Any root R or any parent P has no more than 2 child nodes. Getting it? Has no more than 2 child nodes. So suppose that if I say the binary tree starts off from 5, correct? How many nodes I can have? I would be saying that, okay, let it have exactly a single node 4 it is connected to. Correct? And suppose that it is connected to yet another node 6. Works. Is there any violation so far corresponding to the nature of binary trees? Whatever may be the root, 5, it is connected to 2 nodes. 4 is connected to how many child nodes? Tell me that. 4 and 6 are connected to how many child nodes?
0.
0, right? So I think the properties for any of the nodes is validated. Any violations so far?
No.
Okay. So from 4, how many more nodes you can try connecting? Suppose that I am
No.
connecting just a single node, 2. And 6, I would be connecting just another node, let us suppose 1. Is it still a binary tree?
Yes.
Okay. No problem, I feel. No problem. All clear so far? Let me know. All clear? So
Yes.
this is the nature of binary trees, right? Where any root R, any of the node n, to be more specific, has no more than 0, 1 or 2 child nodes. At max 2 child nodes can be there, not more than. Fine? Fine? Okay? Okay then. This part is done. Fine. Can you tell me one thing? Inside a binary tree, right? If there are L number of levels, inside a binary tree, there are L number of levels. This is my level 1, level 2, and level 3, suppose. What is the maximum number of nodes it can have? How many levels are there? These are the first node is a part of level 1. The next 2 nodes are a part of level 2. The last 2 nodes are part of level 3. If there are overall 3 levels, what is the maximum number of nodes inside the binary tree we can have?
L
Tell me
into
that.
2 plus 1.
Okay, if L
Then,
equal to 3, right? L equal to 3, then this is my structure that I can have max. Fine. How many nodes we are getting? 7. Can I
mhm.
just say what is the maximum number of nodes I may be having? 2 to the power L minus 1 works.
Okay.
Works. If there are L number of levels inside a binary tree, I would be saying maximum number of nodes it can have is 2 to the power L minus 1. Here, each and every level is completely filled, if I am not wrong, is it? Inside the binary tree, each and every level is completely filled. Any more nodes that can be accommodated? I don't think so.
Mhm.
Okay, what kind of binary tree it is? What kind of binary tree it is? Can you let me know on this? This is what you call as perfect binary tree.
Okay.
This is what you call as perfect binary tree. Okay, now let me know whatever was the previous structure, 5, 4, and 6, and 2 and 1, whatever I have drawn. What kind of binary tree it is? Can you let me know on this? What kind of binary tree it is? Can you let me know? Here, see, what is the observation? Only the last level is not completely filled. Am I correct? Only the last level is not completely filled. Getting it? Rest all the levels are completely filled for us. Is it that? Whatever may be the maximum number of nodes from level 1 till level L minus 1, they are all completely filled. Only the last level is not completely filled for us. Fine. Fine. What kind of binary tree it is? This is what you call as the complete binary tree. Complete binary tree. Okay, I'm sorry. Okay, fine. No, no, no. This will not be the complete binary tree. Let me know. Let me specify why. Because yes, 4 is there, right? 4 is connected to 2. Entire level, whatever I'm having corresponding to that of your last level, right? If it has to be a complete binary tree. If this is a complete binary tree, right? Then the leftmost nodes, whatever are the slots available, there are 4 slots. Am I correct here? Am I correct here? There are 4 slots in terms of nodes that needs to be filled. So see, if it has to be a complete binary tree, what is the constraint of a complete binary tree? The last level may be filled, the last level may not be completely filled. Fine. Now, if the filling has to be there, how that has to be? Then the last level from the leftmost nodes, they needs to be filled up. Then only any of the rightmost node can be filled up. Okay, corresponding to a complete binary tree. If you are to fill the last level, right? First, the leftmost slots would be filled. Then only I can go to the rightmost zones. The righter nodes can only be filled if and if suppose all the leftmost previous positions have been filled up. If you are getting some structure like this 5, 4, 6, 2, 3, then only I can term it as a complete binary tree. Okay. The previous one, whatever I have taken, 5, 4, 6, 2, and 1, right? Although this is a binary tree, this is a B tree, sorry, binary tree. Correct? That's fine. All the properties are getting validated, but this is not a complete binary tree in our nature. Because before filling the previous two lefter slots, right? The one has been filled up. So the definition is getting violated. Complete binary tree, inside a complete binary tree, what would happen? Last level may or may not be completely filled. But if you are to fill the last level, first the leftermost zones would be filled, then only the rightermost positions can be filled up. That's it. Any doubts? Let me know. Corresponding to the definitions, any doubts you people are having? Any doubts, anyone? Let me know on this.
Perfect binary tree and binary tree and complete binary tree both are same, right?
Perfect, no, as I said, right? Complete binary tree, the last level may or may not be filled. Perfect binary tree, all the levels would be completely filled. Getting it? All the levels would be completely filled. There would be no slot that would be left for you. Inside a complete binary tree, however, there is a constraint. If you are filling the last level, from the leftmost available nodes only, I have to fill the slots. Then only I can try visiting the last available slot and try visiting it.
Okay.
Correct? Then only the complete binary tree comes into the picture. It's that the last level may not be completely filled, but if it is filled, from left to right, the filling has to be there. That's it. In a perfect, every of the levels would be completely filled. There would be no slot that would be left for you. Okay, that's it. Any more doubts? Tell me that. So in terms of a complete binary tree, right, we get a structure going forward. That is what we call as heaps. We'll see that later on. Okay. We'll see that later on. Are the definitions clear for everyone? Let me know. Corresponding to binary trees, are the definitions clear?
Yeah.
Okay, then let's see a little bit on the traversals. Let's see a little bit on the traversals, right? What kind of traversals corresponding to a binary tree you know about? If this is my binary tree, 1, 2, 3, afterwards, let that be 4 and 5. Let that be 6. What kind of traversals you know about binary trees? Let me know on this. What kind of traversals you know about? How many traversals are there? Most common ones are what? Pre-order, pre-order, and then what? Pre-order, post-order, right? And afterwards, there is an in-order traversal. Correct? Suppose that one is the root of my entire tree. Can you let me know what do pre-order means? How to go ahead and perform a pre-order traversal? Tell me that. Okay. How can I try visualizing corresponding to pre-order? Let me know. See, for pre-order, what we are to visit, if you are visiting any subtree, you are right now visiting any subtree, right? First, corresponding to the visiting, you have to visit the root. First, root needs to be visited, then its left child, okay? Then its right child. Correct? Getting it? If you are visiting any subtree and this is rooted at node R, subtree is rooted at node R. How to visit that? You first visit the root, then go to its left child, then go to its right child. Correct? This is how the sequence of visiting inside the pre-order looks like. Can we start visiting? You have to start visiting all the nodes, whatever I'm having from the root itself. How to go ahead? Let me know. How the pre-order traversal should be looking like. What are your thoughts onto that?
I think one and
Okay,
one of
first, start off from one. Start off from one. So, right, if I'm standing at one, first one needs to be visited. Then I think after one, two, two and three can be visited, right? This is how it is looking like. So, first one would be visited, done. Next, what would be the thing? After one,
two.
where should I go? I should jump on to two, its left child. Fine.
Yes.
I should jump on to its left child. Okay. So see how the sequence from here would be carried ahead. Can you let me know what would be happening here? If
I
you are
think
trying to
4,
visit
5.
2, if you are trying to visit 2, then after 2, you have to give priority to 4 and 5. Am I correct?
Okay.
Once 2 has been visited, I am bound to visit its 4 and 5, its child nodes. So first 2 would be visited, then what would happen? Then what would happen? 2 would be visited, then the flow would be going back to its left child 4. Then 4 would be visited. Any left child of 4 is there? Any left child of 4 is there? No. Any right child of 4 is there? No. So you go back, the flow goes back to 2. 2 has been visited, 4 has been visited. So after 2, 4 has been visited, now the flow is coming back to 2. Then what would happen next? What is the left thing? If I am standing at 2, then after visiting 2, I am bound to visit 4. I am bound to visit 4. After 4 visiting is done, I am going back to 2. What is left for 2 to happen? Visiting its right child? Visiting its right child, then 5 would be visited. Okay, so I think entire corresponding to node 2, wherever I was visiting, this node has been visited. Its left child, right child, both has been visited. You go back to node 1. You go back to node 1. Then what is happening? After node 1, I am left off to visit its right child. Node 1, its left child, its node 1 and left child has been completely visited. My priority now would be shifting to visit its right child. My priority now would be to visit its right child. Okay, 3 would be visited. 3 doesn't have any left child. 3 has just its right child. So my priority shifts here and 6 gets visited. That's it. No node is left. This is my pre-order traversal. What is the observation in as a whole you are getting from here? Tell me that. What is the observation of pre-order traversal that you have got from here? In general,
The
how can I try defining this?
the whole left tree is traversed and then right side.
Exactly. If you are visiting a right, if you are visiting a route R, right? If you are visiting a route R, after visiting the route, you visit its entire lefter subtree. Getting it? You go ahead and try visit its entire lefter subtree. Once the entire lefter subtree is done, you come back and you try visiting its entire righter subtree. Am I correct? Am I correct? Am I correct? Now see, since this is the binary tree for us, right? Any root can have at max 2 childs. Since this is a binary tree for us, any root can have at max 2 child nodes. What are they? The left child and the right child. Okay, it may be possible that left child does not exist or the right child does not exist. If both does not exist, then definitely that's a leaf node for us. Correct? So my root is bound to have any of the root, any of the node n. If that's the root of a subtree, it can have at max 2 child nodes, left child and right child. Not more than that. Fine? Not more than that. Getting it, all of you? Okay. Now suppose if you are standing at the subtree of root R, how to visit in terms of pre-order traversal? First you visit the root R. After it has been visited, you straight away go and try visiting its lefter subtree. Then you straight away go and try visiting its righter subtree. Both. First, all the nodes of the lefter subtree would be covered. Then only I would be trying to visit the righter subtree. That's what I'm going to do. Correct? Okay. So if suppose from R, if I'm standing at R, from where do its lefter subtree starts off? Can you let me know? One has been visited already, right? Then its entire lefter subtree needs to be visited. Then I think the entire righter subtree would be visited. So where do the lefter subtree of 1 starts up from? Tell me that. From where do the lefter subtree of 1 is starting? Is it starting from the left child of 1? Similarly, the righter subtree is starting off from the right child of 1. Tell me that. Is it happening? Is it happening? If you are standing at any of the subtree's root, you have visited that subtree's root. Its lefter subtree starts off from the lefter child. Its righter subtree starts off from its righter child. Getting it or not? Is it clear for everyone? Is it clear? So that's why we say once you are visiting, how did we just visualized? Just a moment. Yeah. If I am right now visiting any subtree's root, after visiting this, I would be first going to its entire left-hand subtree. The start point of the left-hand subtree is the left-hand child of the root, wherever I'm standing. Then I would be going on to visit its right-hand subtree. Its root is residing at the right-hand child. That's it. That's it. Fine. Okay. What else we are to check here? Just a moment. Give me. Let me plug on my charger once. Just a moment. Okay, yes. Can we start? Fine. So how do we define it? If you are right now, what is the overall analogy? If you are standing at any of the subtree, right? If you are trying to visit its root, and from here I am to visit its left subtree via its left child. Okay. And from the root onwards, after the left subtree has been visited, you try visiting its right subtree from its right child. The root of the left subtree is from the left child of the current root. The root of the right subtree of my current root is via its right child. Correct? How do we define it? This entire structure is the sequence of visit to root, then left child, then left subtree, then right subtree. This is recursively true for all nodes. Okay, recursively true for all nodes. That's it. That's it. Correct? That's it. So how would you go ahead and try implementing the pre-order traversal? Any of the approaches that you know, tell me that.
First, we can try to visit the leftmost child of the left subtree, right? That is going to be the first thing that we
Okay,
to
so
achieve.
suppose that I define a function pre-order traversal, correct? You are defining, and here what is the requirement? Where from where do the root of this tree is starting off? This is what I require. Am I correct? Nothing else. So if suppose root is at null, am I correct? Root is at null. Definitely there is no node in that case. There is
Mhm.
no node. That's why root is at null. Then what I am required to do? Then just return from here as it is.
Right.
Just return. Do nothing. Just return. Okay, then what else I require? If suppose this is done, this is not the scenario. There's definitely one or more than one nodes inside my entire sub tree. Then what I'm required to do? Tell me that.
First, we can print the root
Okay,
node
so just
itself.
print the root. Just print the root. Whatever
Mhm.
may be the value of my root, just print it. Print root's val. That's it. Then what else I can do from here? Printing it,
Now,
that means I have visited that. Just the
yes.
analogy. What else?
Now we'll go
Then
to
can
the
I
left
just say
mode.
go ahead and try performing the pre-order traversal on roots left subtree. So I would be just saying access roots left child. Okay, and from here onwards, pass on the roots left child address recursively to another pre-order function call. This function is responsible to visit your entire left subtree after the root has been visited. Works once this task is done, what I am required to do next? Tell me that. Recursive function call. That means it is once this function call is to be completely done, my entire pre-order traversal for the left subtree of the current root would be done. After this execution is done, what I am required to do next? Tell. Perform the pre-order on what? On the roots, writer subtree that is starting off from the writer child. Once both are exited, we are done. After the current root, once the entire left subtree is visited and the writer subtree is visited, we are done. Exit the function. That's it. That's it. Works? Tell me that. Does the implementation works? Tell me that. So suppose how it's gonna work in our case. Let's see. So let the overall tree be 1, 2, 3. Let there be 5. Let there be a 6 here. Okay. And let us have another 4 here. As per you, how the overall execution of the function call would be taking place? Tell me that. You started off from the root itself, right? Root is not at null for us. Current root is not at null. I am trying to say that visit the entire subtree rooted at the main root. Entire tree is a subtree of itself. So visit all the nodes that is rooted at node 1. Then from here, what should I do? First function call condition is not true. Root is not null, so I would be visiting the value of 1. Printing the value of 1, none. Then I would be saying call the pre-order traversal on the entire subtree that is starting off from node 2. Getting it? That is starting off from node 2. What is the start point? What is the start point of the left subtree? Node 2. Node 2 is what? The left child of node 1. That's it. A node inside a binary tree can have at most two child nodes, the left child and the right child. That's the analogy. So I would be passing on straight away. Whatever are the contents that is starting off from the left child of my current root, go on and try performing pre-order traversal on that. Okay, go ahead. I think in the same manner, if pre-order is getting applied on the entire tree, right? Pre-order is getting applied on the left subtree and right subtree as well. First 2 got visited, then 4 got visited, then 5 got visited. Am I correct? First 2, then the content of its left subtree, then the content of its right subtree. The sequence is again recursively same for each and every subtree, whatever we are following. Okay, so I straight away said that, okay, perform the pre-order traversal that is rooted at node 2. Correct? Again, so you made a new function call. You made a new function call here. Right now, if I'm standing here, root is not at null. The root I have provided for this particular function call is the address of 2. That is not null. We have a valid node. Print the root's value. So 2 would be printed. Perform pre-order traversal on the left child of pre-order traversals on the left subtree of 2. You're standing at 2. Its left subtree starts off from 4, the left child of 2. Perform pre-order traversal on it. Okay, you visited another function call, recursive function call we are having. Then what would happen is that 4, this condition is not null. This condition is not null. Then I would be saying print the value of the root, that is 3, and it would again call 4 does not have any left or right child. So both I can say its left and right child are rooted at null. The left and right child nodes of node 4 is rooted at null. No address. No address. What would happen from here? What are your thoughts? What would happen from here? You call on. After printing 4, you would be calling pre-order traversal on the left subtree of 4 that is rooted at null. Okay. So if recursive function call is being called here, then what would happen? This base condition would be hitting root equal to that of null, return. It would be returning to its previous function call. Now afterwards, after printing 4 and printing the lefter subtree of 4, this function call would be called print the writer subtree of 4. That is also rooted at null. We will hit the base case, it would be returning. And once the entire subtree of 4, that is the only node 4 itself, has been visited and printed. Okay, I don't think so. This is 3, but rather than 3, this would be 4. Okay. Once the entire subtree of 4 would be visited, function execution would be hitting the ending bracket. It would be over. You would go back to its parent node 2. The function call would be going back to its parent node 2. 2 was waiting for its entire lefter subtree to be visited. So 4 has been visited and printed. Now it would go ahead and try executing the entire writer subtree visiting. So it would be going ahead and calling recursively to perform pre-order traversal on its writer subtree. From where do the writer subtree of 2 starts? Its right child. So address would be provided, and then what would happen? Tell me. And then what would happen? Tell me. Then what would happen? First, it is not rooted at null. Right now, the function call is at node is starting from root node 5. It is not at null. Then what would happen afterwards? Tell me. First 5 would be visited because root is not at null. Then again, 5 is, if I am standing here, the current recursive calls root is standing at the address of 5. It does not have any lefter subtree. It does not have any writer subtree. In other words, its lefter subtree is rooted at null. Its writer subtree is also rooted at null. Correct? If you call recursively on the lefter subtree and writer subtree visits corresponding to node 5, right? The base condition for both the situations would be hitting. It would be straight away returning to 5 without doing anything. And afterwards, the execution of writer subtree visiting corresponding to node 2. This would be over. And again, the flow would be coming back to the node 2. Again, the flow would be coming back to node 2. 5 has been printed. Writer subtree visiting for node 2 is done. Then flow is back here. Flow is back on from wherever it started. Now, corresponding to node 2 subtree, 2, 4, and 5, node visiting is done, lefter subtree done, writer subtree done. The entire function execution would be hitting the ending bracket. It would return back to node 1. It would return back to node 1. Then afterwards, what would happen? Can anyone let me know? Afterwards, what would be happening? Afterwards, what would be happening? Tell me someone. Afterwards, what would be happening? Let me know. What are your thoughts? Corresponding to node 1, entire its visiting of node 1 is done. Entire lefter subtree is done. So I think till this particular function call, for the pre-order that I am to visit from node 1 onwards, we are done. Now it's going to call recursively go on and try visiting in a pre-order way the writer subtree of node 1. That is starting off from 3 itself, the writer child. Then what would be happening? Tell. You have called on for the subtree to be visited from node 3 onwards. 3 and its lefter child 6. Then what would happen from here? Right now the recursive call is standing at 3. Then what would happen from here? Tell someone. Root is not null. So you would be first visiting 3. You would be first visiting 3, printing the value. Then I would be saying call pre-order on. Call to perform pre-order on 6, right? Call to perform the pre-order that is starting off from the subtree of 6. Again, root is hitting here. Not a null node for me. I would be definitely first visiting this. No lefter or writer subtree of 6 is present. So even if I call pre-order traversal on the lefter and writer subtree of 6, it's going to straight away return as it is. Nothing is going to happen much. So I think the lefter subtree visiting of node 6 is done for us. Lefter subtree visit of node 6 is done for us. Lefter writer subtree both. And 6 has already been visited. Corresponding to this function call, ending bracket would be hitting. Automatically the flow would be going back to 3. 3 has been visited. Its lefter subtree has been visited. Last function call. What is it? Perform the pre-order traversal on the writer subtree of 3 that is rooted at null. It does not have any writer child. So no writer subtree. Correct? Okay, the base condition would be hitting here. You would be coming back. And I feel Okay, entire task corresponding to the subtree of 3 is done. Entire task corresponding to the subtree of 3 is done. That's it. Entire task corresponding to the subtree of 3, that would be done. Okay, ending bracket would be hitting. You would be just going back to the node 1, the parent of 1, corresponding to node 1 as well. Right, its entire left subtree, right subtree has been visited, and before visiting them, I have visited 1 as well, as per the definition of pre-order traversal. Correct? So I think ending bracket for node 1 as well would be hitting, and this would lead me back to the main function from wherever the entire function calling has started. So this is what is my entire sequence of in-order traversal as per the nodes looking like. And this is how you have to go ahead and try implementing it recursively. Does that work fine for all of us? Tell me that. Does that work fine? Let me know. You have any doubts how to implement this? You have any doubts? Just keep that into the mind. Once a node has been visited, entire its lefter subtree first needs to be visited. From where do its lefter subtree starts? Its left child. Correct? Okay, then. After the entire lefter subtree has been visited, I come back to the node. Then again from here onwards, I may try visiting the righter subtree from its right child. That's it. That's it. Nothing else. Okay. Is that clear for everyone? Let me know. Is it clear? The first traversal that we have seen today.
Yes.
Okay.
Yes.
Would you be coming up with the can you try coming up with the code of this? I have already written the pseudo code. Would you be able to implement? Would you be able?
Yes.
Okay. What about the in order and post order traversals? How the sequence looks on there? Can you let me know in order? In order traversal and post order. In order, how does it look like? It says that first, if you are standing at any of the root of any of the subtree, it has a lefter subtree further, it has a righter subtree further. Lefter subtree starts up from the left child, righter subtree starts up from the right child. Suppose that. Then how to proceed ahead? How does in order traversal needs to be maintained? I would be saying perform the in order traversal on in order on the lefter subtree, starting off from the lefter child. First perform it. First visit in the in order way the entire lefter subtree of the current root. Then visit the root, then perform again. Visit the in order way. In the in order way, try visiting the entire righter subtree from the righter child of the root. That's it. First the lefter subtree, then the root, and then the righter subtree. From where do the left and right subtree starts? From the lefter child and right child. That's it. This is how you have to proceed ahead with the in-order traversal. What about the post? What about the post-order traversal? Tell me that. Any ideas? Post-order traversal. What needs to be done? First, you visit the lefter subtree, then you visit the righter subtree, then perform the visiting of the root. That's it. That's the sequence. Okay. So if it is pre, then the root comes first. Root, lefter subtree, righter subtree. If it is in, then first comes lefter subtree, then the root, then righter subtree. Then if it is post, then first comes lefter subtree, then righter subtree, then the root. That's how the overall sequence is going to look like. Nothing else. Just adjust the recursive calls accordingly. You're going to get your answers. Fine. Is it clear? Is it clear for everyone? Let me know. Is it clear for everyone? Let me know on this.
Can you give the example for in and post?
Yeah, sure. Let's go ahead. Fine. Let us suppose, let's take the same tree only, whatever I'm having. 1, 2, 3. Let us suppose there is a 4, there is a 5, there is a 6. Okay, what would happen? Before, what does in-order traversal tells us? In-order traversal tells us, right? What?
Left child, root, right.
Left subtree, root, and then the righter subtree. You start off from the root itself, suppose. Then what would happen? Before visiting 1, what needs to be happening? First, the entire lefter subtree of 1 needs to be visited. Am I correct? So you go on to visit the subtree that is starting off from 2, the lefter child of 1. From where do the lefter subtree starts? From the lefter child of 1, that is at node 2. Then what would happen from here onwards? Tell. What would happen from here?
Again, it goes to left.
Okay, before visiting 2, for any node it is true, right? For any subtree, for any root, this particular sequence is true. Before visiting the root itself, I have to visit its left subtree. That's it. Then what would happen from here? Tell.
Then
Then what
visit the
would happen? Then you are standing here. The in-order traversal is actually rooted at node 3. From whatever may be the subtree of 3, I have to perform in-order traversal here. Corresponding to 3, there is no lefter subtree, there is no righter subtree. Am I correct?
Yeah.
So I can visit 3 directly because it's the leaf node. This is the first node I'm going to visit and I'm going to move back to 2. Fine. Entire lefter subtree of 2C now has been visited. Am I correct? Can I visit the root now? I think yes. Now 2 can be visited. Then afterwards what? After visiting 2, go ahead and try visiting the righter subtree of 2, 4. 4 gets visited because no left or right subtree further exists. Come back. Entire subtree of 2 has been visited. Tell me that. Anything is left?
No. Entire
Okay, so
is
I can go back to its parent. Entire lefter subtree of 1C that starts off from 2 that has been visited correctly. Am I fine?
Yeah.
Am I correct? So right now I can try visiting 1. What after? Okay, and after visiting 1, go ahead and try visiting its entire righter subtree. Works?
Yes.
Works? Okay, then what? Then what would happen? Then what would happen here? What would happen here?
Then visit this 5.
Okay. Okay, what would happen here? See, right now you are to visit the writer subtree from that is rooted at node 5. From here, what would happen? Before visiting this node, its entire lefter subtree first needs to be visited. Am I correct?
Yes.
Recursively true for all nodes. Recursively true for all nodes. Before visiting 5, it's lefter subtree. So first 6 would be visited. No, okay, 6, you come back to 5, then 5 would be visited. It's no writer subtree exists. So nothing would be there. You just go back to 1. I think corresponding to 1 as well, lefter subtree visited, 1 visited, and writer subtree also visited. This is the in-order traversal of my given binary tree. Okay. This is the in-order traversal of my given binary tree. That's it. Okay, you perform on the same tree the post order traversal. How that's gonna look like? 1, 2, 5, 3, 4, suppose, and 6. You perform it and let me know what are your thoughts. First lefter subtree, then righter subtree, then the root. You tell me now how overall the post order traversal sequencing would be looking like. Tell me that.
Start from root.
Okay.
Then
Then,
go to lefter subtree and visit the element.
okay, lefter subtree then.
Again, there is a subtree.
Okay, then.
Then print it.
Okay, it's no left or right subtree
No
is
left
there.
or right. Yeah.
So directly root can be printed. So 3 is getting printed first. Then
Come back to root and go to right.
okay, come back to 2 and then go to right. Correct?
Yeah. Yeah.
So 4 would be visited first. Okay, then come back and visit 2.
Yes.
Lefter subtree done, righter subtree done. The root of the current subtree 2 would be visited. Okay, then what?
Yes. Again, go back to root
Okay, go back to root. Yes, done.
and visit writer subtree.
Okay, then I am here. Righter subtree starts off from 5, so I am here.
So there is another subtree. So go back to left subtree.
Okay,
6. Uh,
done.
yeah.
Then,
Come back to root.
yeah, no righter subtree. So 5
Yeah.
can be visited. Then you come back to 1. At the end,
Root.
1 would be visited. That's it.
Yeah.
Fine.
Yeah.
That's
Fine.
the post order traversal. Just you need to adjust the recursive calls. Coding part, will it be, can you people try doing it? Let me know on this.
Yeah. We'll try.
Okay. So what we have seen today, the basics of binary trees and its traversals, correct? And its traversals. Coding part, please try, right? Today. If you are unable to do, tomorrow we'll do it.
Okay.
Works. And we'll take more problems on binary trees tomorrow. Okay. Any doubts if people have? Tell me that. Any doubts? Any doubts, anyone?
No, it's clear for me.
All of you? Only 2 people are coming.
Yes.
Okay, then try performing. Few more classes I think would be required for this is just the first class. I think 2-3 more classes of binary trees would be there. And once this is done, we'll move on to the topics of graphs. Fine. We'll move on to the topics of graphs, and afterwards we'll see 3, 4, 5 classes of that also would be required. I think, and afterwards few standard problems of backtracking, and I think your syllabus would be over corresponding to DSA. Because backtracking, there are very few problems that are there. Okay, I think DP is also pending, right? Dynamic programming. Okay,
Yeah.
but we
Right.
have time, I think, till April full. And moreover, we would be having 3 classes each. Okay, I just wish to ask, just a moment.